In this video I'm going to talk about the class of implicit Runge-Kutta methods called DIRK methods. Okay, so DIRK stands for diagonally implicit Runge-Kutta methods. Now these are a class of methods that have a butcher tableau of this form. So we've got our B values down the bottom as normal. So if we've got S stages, we have B1, B2 up to PS. We've got our C values, there'll be S of them. Now for our A values, we have A11, we have a lower triangular sort of matrix arrangement. So if I just write it out completely, so that's S1, that's S2, all the way to ASS. Okay, so we have this type of arrangement. So notice up here, all of these A values are 0. Now this is an implicit method. Okay, so if I was just to write out what our what the stage values are, so I have f of Tn plus C1H, I have Yn plus H. Okay, so I'd have, this is just expanding out the general form, A11, K1. Okay, so that's our first stage. Second stage, notice I've stopped here, I've only used A11 because all the other A's on that row are 0. So Tn plus C1H, In plus H, and this time I'll have a couple of okay, keep going down all the way to KS C1H. I'm going to be a bit lazy here, I'm just going to write it in summation form. So that's J equals 1 to S Aij, sorry, I should say A S J KJ. Okay, now so the reason I wrote these out is just to remind you that the K1 here does appear on the right hand side, and K2 here again appears on this right hand side. So these are implicit equations, but what the benefit of DIRK methods are is usually with any other type of implicit method we'd have to have an iterative solver on all of our K values at the same time, which can take more iterations. Now with a DIRK method, it means we can iterate this first equation to calculate for K1, and then we know what K1 is, so then we can use K1 and just iterate the second equation here. Okay, so it means we can calculate K1 and K2 in a sequential order, which is actually more efficient than other type of implicit Runge-Kutta methods. If you're a little bit confused about that, I suggest you check out the video on applying implicit Runge-Kutta methods to solve an initial value problem. Okay, right, so how do we derive DIRK methods? Well, coefficients of a DIRK method are chosen, so all the coefficients are chosen to satisfy the BK condition. So coefs satisfy the BK condition and the CK divided by 2 but rounded down to the nearest integer, and another condition which is the transpose of the B vector times the A matrix times our C vector is equal to 1 over K factorial. So, well, I should also mention, but when we say a B vector, we assume a column vector. So, in the butcher tableau, it's always written. Across, but we assume that our B and our C values form the vector column vectors. Just sort of common or standard way of expressing it. Okay, so we have these three order conditions. So we have the BK, we have the C half K rounded down, and we also have a set of order conditions here. Right, so I'm going to have a look at have a go at doing the example in the notes. So this is example 3.4. Right, so and the example asks us to derive a two-stage DIRK method. So if we've got two stages, what we can know is our butcher tableau will look something like this. So we'll have our B1, B2, we'll have our C1, C2. Okay, and remember, so this is going to be 0, and we're going to have 3 others. But from the row sum condition, we know that this has got to be equal to C1, because the sum of our first row of our A matrix has got to equal to C1. Well, if A12 is 0, that must mean A11 is equal to 0. Okay, and down here we've got A21 and A22. Okay, so for a DIRK method, we have 1, 2, 3, 4, 5, 6, 7 coefficients to solve for. Okay, so how do we solve for those 7 coefficients? Well, let's look at the order conditions. So remember the BK order conditions for a two-stage method. B1 plus B2 is 1, and B1 times C1 plus B2 times C2 is equal to 1/2. We don't have to go any further than that. Actually, yeah, let's go. I was about to say that we don't have to go any further, but we do. I'll explain why in a minute. Okay. Okay, with the derivation of the Radal and the Radal method and the Gauss-Legendre method seen if you watch those videos, we already had a method for solving for C1 and C2, so that cut down on the amount of unknowns we have. But because we do have these as unknowns, we do have to go a bit further with these conditions. Okay, so that's a BK condition. Okay, we also need the CK condition, which, remember, these were the row sums, so we had A11 plus A12 is equal to C1. But remember, A11 plus A12, we've already accounted for it up here, so whether we need this, you know, I've put it here for completeness, but we might actually need this. And we also have the second row sum condition, so A21 plus A22 is equal to C2. And finally, we also have, I just remind us, it was a B transpose times A times C is equal to 1 over K factorial. Okay, so this will give us, if we have B1, so what this means is we have B1, B2. Okay, I've got our A matrix. That's 2. Oops, should be 2, 1 there, and 2, 2. That's times by our C vector, C1, C2. Okay, so if I just see what this is, so we've got 2 by 2 times 2 by 1, so that'll give us 2 by 1. So that'll be C1 squared, and that'll be C1 A21 plus C2 A22. Okay, so that would be B1 C1 squared plus B2 times all of that bottom one. Okay, and that'll be equal to 1 over K factorial. Okay, so in our case, if we want a two-stage method, half 2 round down will be equal to 1 over 1 equals 1. K factorial, oh, sorry about that, yeah, so it should be B2, sorry, B3 factorial, so that's 1 over 6. So our last order condition, which came from B transpose A times C, was 1 over 3 factorial. Okay, that is equal to B1 C1 squared plus B2 C1 A21 plus C2 A22, and that's going to be equal to 1 over 6. Okay, so here we have 1, 2, 3, 4, 5, 6, or, you know, this one's fairly trivial, and we have 1, 2, 3, 4, 5, 6 unknowns. So what we have is we got 6 equations and we have 7 unknowns. So we have an underdetermined system. Okay, we can't possibly we can't solve this without specifying one of these. So all we do is we specify one of these values and solve for the rest. So for example, if we let let's say we let C1 equals 1/4. Okay, I've chosen C1 to be 1/4 because it means we get some slightly nicer values in the butcher tableau, but that's totally arbitrary. So let C1 be 1/4, then the others, so solving gives, and I've solved this using MATLAB or any other software, so solving gives C2 is this equal to 5/6, B1 is 4/7, B2 equals 3/7, A11 is same as A11 is the same as C1 obviously, so that's 1/4. Don't need to solve for A12 because we've got a DIRK method. A21 solves to be 2/3 and A22 is 1/6. So our butcher tableau looks like this. So it's 4/7 and 3/7. We've chosen C1 to be 1/4 and C2 is 5/6. We'll have 1/4 there, 0, 2/3 and 1/6. And that is a third order DIRK method. The reason I say it's a third order DIRK method, there are lots of different ones based on what we chosen for any one of our unknowns. And now, as I mentioned earlier, I chose C1 equal to 1/4, just so that these are all nice fractional quantities.